All right, so for today, I kind of swapped the order a little bit about the notes template, but if you already downloaded it, don't bother. You can just swipe, between the pages. I wanted to adjust the sequence slightly. So the plan for today, I want to start with two mathematical induction examples. So there's something maybe still fresh from our lectures on Monday. So let's do two examples here. One will be mathematical induction on graph. The other one will be on tree. Okay, and then after that, I want to give you guys a little bit of maybe some very quick walkthrough about the test cases that you will see a lot in assignment number 1. So this will be kind of the complexity you have to know how to comprehend also for your programming test. Right? I will take a look at that and to see how we can visualize it. And then after that, hopefully we'll get enough time. I want to revisit the deletion example that we didn't really manage to do last time. If you remember last Thursday, we kind of went through the steps for deletion and how we are supposed to fix the balance after that, right? We can talk about, there are two cases over here. So that's something I'd like to go over with you as much as I can. Maybe at least, there will be 2 rotations that's going to be expected, I can tell you, but at least we can do the first rotation altogether, okay? But you will see the idea. Okay, so that'll be the plan. But I would like to start with mathematical induction. So important to get right, all right? So you can also find this property here also on the slides, right? So there are 4 properties in total. I want to focus on just one of them today in the tutorial. I'll talk about the other 3 in the beginning of Monday's lecture, okay? Let's just get clarified about the language first, because somehow the property can specify in English, but we want to make sure we understand exactly what the property is saying, okay? So we have undirected graph, no directions, and that's it. And then we didn't say anything about parallel edges or maybe self-edges. We didn't say that, right? So we just live with, just as long as the graph is undirected, that's the graph we have to consider in the proof. So we got a very standard acronym. We got number of vertices will just be n, number of edges will just be m, all right? And let's focus on just one property for today, okay? And then we'll talk about the rest on Monday, okay? Let me highlight this property over here. Okay? So we are saying that the number of edges will be equal to the number of vertices minus 1 if the graph is a spanning tree. All right? And let's recall exactly what a spanning tree is. Can anyone remind us about what would be the property we have to? Oh, in some ways it's not fair because I asked you guys to study over the weekend, right? It's not even close to the weekend, right? If anybody can kind of remind us, if you can recall, what would be the property that should be true for spanning tree? Diego.
So I believe it's a subgraph that has all the nodes.
All the nodes, that means spanning, right? I agree. Well, obviously spanning tree got to be spanning. Otherwise, why would it be called spanning tree? Okay, awesome. Let's just remind ourselves, and then I got another important question to ask, okay? So this one here, definitely it should be spanning. Also, I can tell you that it should be undirected. What else? Connected, I like it. Okay, awesome. Maybe we're missing one more. Doesn't have a cycle or acyclic, exactly. All right. Acyclic, very good. Because in the actual property here, it doesn't say anything about these 4 properties. That's something you should really recall from the definition. And one more thing to say that can also help you study over the weekend. In order to be a tree, it should be undirected, it should be connected, and it should be acyclic. But it doesn't need to be spanning, for a tree, right? But since we say it's a spanning tree, we are just adding some extra qualification. Okay, that's the first thing I want to sort out. Second thing, can we try, let's say this is a predicate, Q. This, let me say it again. Let me just make it more obvious. This here is more like a predicate, true or false. This part here, G is a spanning tree, is another predicate. Let's call it P. When I say Q if P, what exactly am I saying? formulated in predicate or propositional symbols? Yeah, go ahead. If P then Q, or how about use the standard propositional operator, right? You can use conjunction, disjunction, implication, if and only if.
P and then the arrow and Q.
P implies Q in this case, right? Okay, very good. That's something you guys, if you're not feeling comfortable, you should really look at the math review lecture, okay? Very important. When I say, I'll put it aside, okay? When I say Q if P, I'm really saying P implies Q. That's what the property is stating. Whether or not Q should imply P bidirectionally, we're not too sure. Okay? I can put a question mark. In the property, we are not concerning about Q implies P. Okay? Meaning that we have to assume if it is a spanning tree, then this must follow. On the other hand, we didn't say anything in the property. If this was the case about the relations between number of edges and number of vertices, then this should follow. We didn't say that. But we can talk about it a little bit later. Okay? So you can think about in the test or exam, I can formulate a property either way. In which case, you got to see exactly which one can be maybe proof or disproof. All right? All right, for these three, we'll look at them on Monday. All right? Just not relevant for now. All right? I can tell you this one here can be proved. Right? It's actually good. So let's now try it. Right? Mathematical induction. Well, remember we actually got several steps, right? Number one, we should really have some base cases. Okay? So we're going to perform a mathematical induction. In this case, again, I think many cases you can simply start by saying, I want to do a mathematical induction on the number of vertices, because vertex can exist by itself, but not the edges, right? You cannot simply have an edge without n vertices, as we said in the lecture. Okay? So we're going to say, we're going to conduct mathematical induction on the number of vertices. Okay. Over here. Of course, over here, you can think about like an empty graph. Empty graph is definitely like a very special case, right? So when n is equal to 1, for example, right? So here we talk about maybe larger than or equal to 0. So this one will be more like a trivial case. You can think about empty graph. You simply just cannot violate any of the 4 properties. So it must be a spanning tree by definition. It's like an empty set can satisfy any property, right? Oh, actually, I meant to write over here, n equals 0. Okay. Empty graph does not violate the 4 conditions over here, 1 to 4. It is a spanning tree. Right? It's kind of trivial. But of course, if I didn't want you to consider this case, I could have said it's like a non-empty graph. I could have said that. But since I didn't say that, you should consider empty case as well. Okay. All right, let's try maybe a few more base cases. When n is equal to 1, that would be the very famous one-node graph. Okay, over here. Now, in this case, what exactly do we have over here? So here you can see that n is equal to 1. Guys, I do apologize. I noticed one mistake, which is good to correct it now, okay? What I said earlier about here, empty graph, where we got v would be equal to 0 and e equal to 0, all right? In this case, you can see that if we apply this formula here, 0 equals 0 minus 1. It's not the case. So this property is not exactly satisfied. I do apologize. I forgot that point there. Okay. So let's modify this slightly. Okay. Not empty. That'll make it a little bit easier. Okay, I'll fix the slide as well. Okay, I just noticed that point. Okay, so here, not to be considered. Because even though empty graph is a spanning tree, but in that case, the property is not satisfied. So it got to be non-empty. Okay, starting from that case. Okay, so what we say is it should be exactly larger than 0, not empty. Okay, so this one here, n equals 0, not considered. Okay, good. So now let's talk about n equals 1. So in this case, we got only the vertex, but without any edges. So now in this case, the n will be equal to 0. First of all, is this a spanning tree? Apparently, it is spanning. Well, it actually involves all the vertices, which is just one vertex. And then it's also undirected. There's no edge. And also connected, well, it's just node by itself, right? There's nothing about connection. And also acyclic, there's no cycle, right? And in this case, you can see 0 equals 1 minus 1. All right, that's good. Let's do a few more, a couple of more, okay? Yeah, go ahead. Because somehow we just want to add, I think I just want to make it a little bit simplified. So I'm just adding that extra assumption for us to consider. So we're just saying that the graph is not empty.
But it is still a spanning tree.
Empty graph should be a spanning tree, I think. Okay. Yeah, I'll try to make re-emphasize this point maybe again on Monday. Yeah, I think it's actually always good to consider in the special case when you got empty graph. Yeah, I'll talk about it again. Yeah. But for now, to make the proof a little bit simpler, let's not consider empty graph. Good. Okay, n equals 2. And then we got one node over here and one node over here. Now you want to think about, now, given two nodes, how can we create a spanning tree from there, right? Well, apparently you can draw the edge, for example, right here, that'll create a cycle. If you draw it here, it's going to create a cycle. Not good. So the only way to make it work is by creating an edge in between. Right here. Right? That's the only way. So what we got is n equals 1. So in this case, 1 equals 2 minus 1. Right? So this property also holds. Very nice. Why don't we do one more? Okay. So let's say n equals 3. 1 here. 2 here. Let's say 3 here. All right, so here, if I want to create a spanning tree, I want to make sure, let's connect these two. And then I just need one more edge to make sure the third node is also connected to the rest. So I can either go this way, or I can go this way. But I cannot go both. Because if I go both, I'll get a cycle. All right. So now in this case, I got n exactly equal to 2. So now 2 equals 3 minus 1. Okay, so these are the base cases, right? But now, before I get to the inductive cases, let's now think about this property here. The properties simply say, given that it's a spanning tree, that implies this relation holds. Can we try the other way? If I say, if the number of edges is exactly the number of vertices minus 1, does it always imply it is a spanning tree? You might already be kind of come up with one counterexample already, right? In order to disprove it, you will need to need a witness, right? Okay, let's give it a try. So let me put it aside, okay? Let me put it right here. Let's say I have 4 nodes. All right? So I want to make sure the number of edges is exactly number of vertices, which is 4 minus 1. So now I'm going to have 3 edges, right? If I do 1, 2, and 3, it is a spanning tree. However, if I do 1, 2, and 3, it is not a spanning tree. Because what did I violate? Yeah, definitely it's not connected. Also, I have a cycle, right? Okay, so this is a witness for the other way of the implication doesn't hold. Okay, that's an aside. Okay, so you got to be careful about which direction am I asking, in the actual evaluation. Okay, so this is a witness for, right? Remember, this is Q and this is P, right? For Q implies P. That is why the property itself doesn't really say if and only if. Only one way will work. All right. All right, so now we're good with the base cases. So let's now try to look at inductive hypothesis. Okay. So let me state it here. Inductive hypothesis. So now I can make it a little bit more logical, like an implication sign. Okay. Given that it is a spanning tree with the size larger than 3. Okay. So let's say G is a spanning tree with the number of vertices strictly larger than 3. Just strictly larger than the base case. That would imply the left-hand side. That would imply the number of edges, which is m, equals n minus 1. Right? Of course, here, number of vertices, we'll just say that's n. Right? Just remember, sometimes I may not actually mention both. You should know. That's a convention. Whenever we talk about number of vertices, it should be n. Number of edges should be n. So this will be the inductive hypothesis, we assume. And we're going to use it right here. All right, so far so good? Okay. Now why don't we let you guys take 1 minute? All right. So now, if you recall the only mathematical induction example we did in the class, once we have stated that, what did we do? We kind of draw a cloud, and a cloud somehow has the property that will satisfy inductive hypothesis. And then after we have got a cloud, we have to somehow extend the cloud to be something bigger. Why don't you take 1 minute to see if you can sketch any idea along this line, and then we'll do it together, right? So this exercise over here turned out to be actually simpler than the example we did in the lecture. The math part is very trivial, but I think that the most important thing is for you to do the next step, which is to draw some cloud, which we assume to be true by inductive hypothesis, and then to extend the cloud to be just some strictly larger spanning tree and see if the property will still hold. Right, that's the idea. Why don't we pause for just 1 minute? You guys can think about, and then we'll look at the diagram. So I'll just write one line here. Consider a larger spanning tree. And this is something you have to draw. All right? So I can start with a cloud, first of all. Like that. All right? This cloud here is a spanning tree. And this spanning tree, whatever property it will satisfy, is guaranteed or assumed by the inductive hypothesis. So what exactly do we know about this spanning tree? We don't know exactly how it looks like concrete shape, but we do know about what property it should really satisfy, right? It's a spanning tree, so that means the consequence over here should be true. So what we know is, number one, the number of vertices will be more than 3. And also, the number of edges will be the number of vertices minus 1. Okay, that one I can write a little bit better. Otherwise, it's a bit difficult to see. Number of vertices minus 1. And so this will be n. And this will be n. Agree? This cloud here. How exactly it will look like doesn't really matter. We know that it's assumed, it's guaranteed by the inductive hypothesis. It's a little bit like, whenever you want to program recursively, when you make a recursive call, you have to be confident that that method is going to return back to you the correct result, you assume. Yeah. Some instructors like to think about whenever you want to make a recursive call, you're basically asking your friend to do something for you. You trust your friend. So here we're trusting the inductive hypothesis. Okay, that's another analogy. Okay. So another question is, what would be the minimum possible way to make a larger spanning tree? That one should be quite obvious, but go ahead.
Add a single node.
Add a single node, only node, and okay, sure. So what I will do is, yeah, okay. Of course, let's draw that. I totally agree with you. That's something I think anybody will just intuitively try first. But the thing is, once we have outlined that larger graph, we're going to justify that's still a spanning tree, right? That's something we'll get to, okay? So what we have is, let's say we add one node right here. Let's call that x. And then I will simply pick some vertex from the spanning tree. Just pick one. And then connect them. All right, so pick one existing node, any one of them. You got n different choices you can take, and then connect with a new node. Okay, and then think about this is new cloud that we have. This one here is the new cloud right here. So now, why is this still a spanning tree? What you want to ask yourself is, oh, do you want to say something before I say? How about that?
No, I was going to say it still encompasses every node and it still does not have any cycles.
Yeah, exactly. Somehow you want to reevaluate all the 4 properties, exactly, right? Okay. So you want to think about adding this connection here. Has it actually allow us to really satisfy the spanning property? Yes, because now we have covered also this node in part of the subgraph. And also, has it maintained to be undirected? Yes, because this direction here, well, there's no direction here. Has it been connected? Of course, because this new node is also connected, right, to everybody, to every node else. And also this one here, we haven't really created any cycle as well. Okay. So let me just write it down here. Over here. Number 1, this one covers all n plus 1 nodes, including x. Number 2, remain undirected. Okay, number 3, the new node, x, is now connected to every other node. Number 3, okay, let me go a little bit further. Because we know that all the nodes within this old spanning tree is connected to each other. X now is actually connected to one of them, so of course they're all connected to each other. All right. Number 4, created no cycle. Because in order to, we know that already this part over here has no cycle. In order to really have a cycle, that means this new node should also connect to another distinct node to create a cycle, but it's not what we are doing. Right? So this 1, 2, 3, 4 over here is also very important. You cannot just make any arbitrary extension and assume it's still a spanning tree. You have to justify. Right? Good so far? All right, let's now do a little bit of math, which is very elementary. Okay. Let me, like before, let me help you a little bit by drawing a quick table. Okay, I'll put it aside here. So what we have is before extension and after extension. So we have before extension and also after extension right here. So before extension, what we have is the n just equal to number of vertices. And, oh, let me put it another way. Number of vertices, just n. Number of edges will be just equal to n minus 1. Right, before extension, it's a spanning tree. Now, the strictly larger spanning tree, so let's call that V prime. So V prime is the number of vertices after the extension. Of course, that would be just n plus 1. Right, which is adding that new vertex. So you can think about this plus 1 over here is the x that we're talking about. And the number of edges afterwards over here should be equal to what used to be the case plus 1, because we're adding this particular edge. And also we know that this one is n minus 1. So that should be n minus 1 and then plus 1. All right, you can see the math here. That already kind of already show you what will be the critical step in the proof. But always good to compare before and after. I think that's the main point. Alrighty, so let's now do the math. So what we want to show is, now we want to show, given that the new extended cloud is a spanning tree, the number of edges after E prime will be the number of vertices after minus 1. This is what we want to show. Okay, let's show it. All right. So what we have is, let's start with, okay, we can see that the number of edges after the extension. Let me just note that too. So E prime will be the number of edges in the larger spanning tree. Okay, and that one there will be just the number of edges before the extension plus 1. All right, and this part here, we can apply the inductive hypothesis, right? Because inductive hypothesis told us the number of edges would just be n minus 1. All right, so that's a critical step. You always got to apply the inductive hypothesis. So we're going to say equal to, by the inductive hypothesis over here, it should be n minus 1 and then plus 1. If you simplify it, it's going to be just n. All right, so far so good? All right. And this one here is just equal to the n plus 1 minus 1. And we know that from before, n plus 1 is the number of vertices after the extension. And that's it. All right. I think it's really the want to show part you want to really get right. And then you want to figure out what exactly will be the E prime and V prime, and then try to work out the math. At some point, you should really apply the inductive hypothesis. Okay. Questions about this one here? All good? Of course.
I just want to know, how did you figure out that that is what you wanted to show?
It's a very good question. The question was, how did I know this is the diagram I want to draw? I would say, since I've seen maybe more problems than you have, I got a little bit more experience. So I know that every time, well, here's the principle, okay? Let me try, okay? I'll try to answer this as accurately as possible. Usually, so let's say you're already given the inductive hypothesis. That's something you're given, let's say for any property, right? And then you just want to imagine a cloud, okay, which is a graph satisfying the inductive hypothesis, okay? So I basically draw the cloud, inductive hypothesis, which is the case right here, and also, which is the case right here, also in the case where, example that we talk about in the lecture, right? That's good. And now, here comes the critical part. How do we extend it? You want to think about what's really the property we're speaking about. Since we talk about spanning tree, so inductive hypothesis already give us a spanning tree. We want to make this tree larger, but still maintain to be a spanning tree, right? So here, this will be the part, will be the minimum extension to make a larger graph that still satisfy the property. Because remember, for inductive hypothesis, we're going to assume like a P of K, and then we want to show that P also holds K plus 1, right? So that's exactly the K plus 1 part, right? Yeah. Okay. Of course, there's something you just want to be a little bit creative. I would say always try. Maybe I can just add a new vertex. Maybe sometimes you can you have to make maybe 2 vertices in order to make an extension. It really depends on the question itself. Mm-hmm. Question.
So is it sufficient to say that by adding a new vertex and a single node connecting it to any of the node in the original?
Oh, you mean to actually explain about extension? Yes, exactly. Yeah, I can write it. I see what you mean. Yeah. I think either you can write it down in the sentence or, okay, consider, okay, how about this? Yeah, I see exactly what you mean. A larger spanning tree by adding a new vertex x and connected to any of the v or n vertices. Okay, that would be enough. For example, if you already got 5 vertices in the old spanning tree, you can pick any one of the 5, exactly 1. Diego.
Is there any reason why in this example you chose to have 3 base cases? Because usually in most mathematical induction proofs you only use 0 and 1 for base cases. But in this case you chose to go n equals 1, 2, and 3.
I would say the number of base cases over here is completely up to like how far you want to go. Right? It's like if you program recursion, right? You can say, oh, my base case could be when array is equal of size 0, 1. That might be just enough. But I may just want to add an edge case to say, well, that's equal to 2. I just want to do a little bit more, right? So I would say, yes, you're right. Typically, 1 or 2 base cases should be enough. But it certainly sometimes might help you to see a little bit more insight into the general pattern once you get to maybe a little bit further. But you definitely want to go like a 10 base cases. That would be too much, right? So I would say in this case, it will have a good reason. Because if you look at right here. This one seems so trivial. If you already got 2 vertices, the only way you can link them is just by, link them, right? But this one here is interesting because now once you have linked one here, you can have a self loop, etc. So you can gradually just see a little bit more pattern to see how the edges should be distributed over the vertices, right? Mm-hmm. Also, it's not wrong if you just try n equal to 4, if you want to see more, right? But at some point, you have to make sure you have the inductive hypothesis. And this lower bound is something that has to be adjusted accordingly, right? You still got to do the same amount of work for the inductive work cases.
So if somebody were to come up with a slightly different inductive hypothesis let's say.
Yeah, that's okay. You can say that greater. Yeah, that's fine. Yes. All right. If no further questions, okay. So we got 5 minutes before halfway. Why don't we do a little bit of the second problem here? Okay. The second problem here requires a little bit of knowledge from 2101, but we already reviewed it, so it should be good. There's only one thing I want to remind you about. What does it really mean for a binary tree to be proper? Okay. So there is something you will see. Okay, I'll show you this. Okay, this is already like a visual-friendly version of the question. But if you look at the actual tutorial, let's read it together. Okay. This one here. Okay, this one here. Okay, we say given a binary tree, not empty, at least one node. Okay, and also it should be proper. Proper means each internal node in the tree has exactly 2 child nodes. It's the definition for a tree being proper, a binary tree being proper. If you have no internal nodes, that's okay. Just external node, that's also fine. Right? So this 2-child policy here is actually only for internal node, not for external node. Right? Well, external node cannot have child by definition anyway. Right? All right. Having understood this, let's now move on. Okay, to here. So we are saying that given that the binary tree is not empty and it's proper, every internal node has 2 children. And we're going to use some notation here. Right? You can think about the number of nodes for internal, the number of nodes for external. All right, over here. Okay? That's why you will see n with subscript I, and also n with a subscript e. And we say that the number of external nodes will be exactly equal to number of internal nodes plus 1. That's what the property says. All right, for this one here, I can also I'll be nice to you. I will tell you that it's a property. We can prove it. But let's now just understand the property first. This example tree here is proper. But apparently that's not empty, right? At the same time, it's also proper. But let's now double check. Let's now work out what will be the number of external nodes. That will be all the nodes without any children, right? You can think about here, 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 and here. So the number of external nodes equals 1, 2, 3, 4, 5, 6. Okay, agree? And the rest will be internal nodes. 1, 2, 3, 4, and 5. Number of internal nodes equals 5. And you can see the property holds. 6 equals 5 plus 1. Also, the tree is proper because you see that internal nodes, 2 children. Internal nodes, 2 children. Internal nodes, 2 children. And these are external nodes. By definition, they have no children. Right? It's proper tree. Okay. Let me make this much smaller, and then we'll do a little bit, and then we'll take a short break and complete it after the break. All right, let's do base cases. Why don't we do base cases, and then we do inductive hypothesis, and then we do a little bit of extension. So for those of you who might be keen to really move ahead, you can try with that, okay? But you don't have to, okay? Okay, base cases. Okay, number 1, let's deal with base cases. Should I try with the empty tree? I shouldn't, right? Because I said not empty, right? Just please notice that, right? And then I can try a singleton, well, like a one-noded tree. A singleton proper binary tree, which means there is only one node, which is external. It's a proper tree because the only node we have is external. which is not subject to the two-child policy, right? So now let's see. So the number of external nodes will be 1. Number of internal nodes will be 0, right? All right, so this one holds because you can see that this one, 1 equals 0 plus 1. All right, so the property holds. Okay, so that's the base case. So Diego, you will like this. We just try one, right? But if you like, oh, question for you. Well, if I want to do one more base case, what should I consider? Should I consider a proper tree with 2 nodes, 3 nodes, or more?
Has to be 3 nodes.
Has to be,
Because if you're going to have children for that first node, it has to be children.
Exactly, okay? So guys, you can take a note for yourself. I'm not gonna write it here. So for example, if you say 2 nodes, that's not good because it's not even a proper tree, right? So this will be the next base case. Good. Oh, what about, let me go a little bit more if you don't mind. This will be base case number 2. What about base case number 3? Well, every internal node should have, well, actually, sorry, I beg your pardon. So let me do it again. So this will be the next one, and then you should add another branch over here. Right, that'll be the next one. Okay, I was going a little bit too far. Okay, yeah, good. All right, inductive hypothesis. And then I'll talk a little bit about, give me about a few minutes. I'll talk about inductive hypothesis, some extension idea, and then we'll take a short break. Number 2, inductive hypothesis. For a proper binary tree of size larger than 1, it is the case number of external nodes equals number of internal nodes plus 1. Okay? External and internal. Okay, simple to state. Okay. What about extension, though? Oh, you got a question? You want to talk about extension?
Question.
Question. Go ahead.
Do we need to extend it? Can we just say instead of singleton proper binary tree, can we not just say singleton proper binary subtree, and then same?
Oh, you're talking about the base case there, right?
Yeah,
Oh, you're about the
the
name.
base cases talk about subtrees instead of the entire tree, and then they work for every case. No.
No, actually, since we are doing induction on the number of nodes in the tree, so you talk about proper binary tree of size 1, and then proper binary tree of size 2, and etc.
Yeah, but every single time we extend the tree, we're taking a singleton node and adding 2, so they fall within the 2 base cases.
Well, I think what you're talking about is not exactly following the mathematical induction pattern. You know, I agree with your intuition. I know exactly what you mean. Yeah, yeah. But we got to do it mathematically, right? Yeah. Mm-hmm. Might be okay to justify for this example here, but not really for in general. Yeah.
Extension?
Extension?
Yeah.
Why don't you talk about it quickly? Yeah.
So if we're going to extend it, then you take we assume that the property already holds.
Let's.
And then we take an external node, add 2 more. So what happens is
Mm-hmm.
the number of external nodes increases by 1 because the previous one.
Oh, you don't need to go too far. Yeah, just about extension. Yeah, very good. Thank you. Yeah, good. All right, let's now, I think your fellow student pretty much captured the essence, but let me visualize it, okay? Let me just draw some diagram, and then I'll give you more details after the break. So, number 3. Basically, what we do is imagine that, well, rather than cloud, I would say cloud usually for the graph, but I would say for tree, make a triangle, because that's a natural shape, right, for a binary tree, okay? So this tree here will satisfy the inductive hypothesis. The number of nodes will be larger than 1. And we know that the number of external nodes equals the number of internal nodes plus 1. All right, so that's by the inductive hypothesis. All right, and now what we want to do is to actually make a strictly larger proper binary tree. what we can do is, I'll write it down after the break. Go to the bottom layer, and then choose the rightmost external nodes, and then convert it into an internal nodes. Okay, let's say, for example, let's say the rightmost external nodes at the bottom level is like this. Let's call that N over here. And then what we want to do is we want to extend, we want to convert that into an internal nodes, which means we've got to give it 2 children. So what we do is we're going to put, let's say, X and also Y. So that'll be the extension. So now I can tell the math part may be a little bit trickier, because now you actually got somehow the number of external node, they both change somehow. But I got to work out exactly how to express that. Right? That's something I'll speak about after the break. Right? We just get the notation very clear, and then everything else should be straightforward. Okay? Why don't we pause over here? All right. So let's write down the actual extension that we're going to do. All right. So the strategy, I'll put it here to the right. Extend the current binary tree by converting the rightmost external node at the bottom level to an internal node. Since I've got a diagram, so it's pretty obvious. I'm talking about, X and Y, right? And the internal node I'm talking about is N, right here. And to make the math actually clear, okay? Again, let's now compare before and after, okay? So now let's talk about some notation here. So we have N, I, and also N, E. So these will be the number of internal, external nodes before the extension. So these two are the measures before extension. And after the extension, let's use a prime. Right? It's also a very standard way to actually create some extra symbol. So it's going to be N-I prime. And also N-E prime. So this will be after the extension. And of course, what we want to show will be the number of internal nodes after the extension. Oh, beg your pardon. The number of external nodes after the extension will be equal to the number of internal nodes after the extension, right? You can see the property here, just prime and prime, right? So that will be something we want to achieve. Right here. Okay. But let's now work it out, exactly what they are, right? That's the tricky part, okay? I'm going to have some side equations over here. Let's first of all work out what this would be, and then work out what this would be, and then we try to see if the equality is going to hold. Okay? So let's start with that one there. So I'll start with, give me one moment. So I'm going to get 1 and also 2. All right? Number 1, I'm going to work out what would be number of external nodes after the extension. All right? You can see that this used to be external nodes, but it's now not external node anymore. So that should be -1. On the other hand, I'm adding these 2 external nodes, so that'd be +2. -1 + 2. All right? So what I would say is number of external nodes before the extension, but now I'm actually going to say -1 and +2. The -1 over here is the n. N used to be external, but after the extension, it's now internal, so -1. And the 2 over here will be the x and y, because now I have 2 new external nodes. Okay? And of course, simplify it. We got number of external nodes before the extension plus 1. All right, that's equation 1. Okay. And we do something very similar. Okay. And then we do number of internal nodes after the extension. Okay. If you think about internal nodes, what would that be? +1, -1, what should we do? +1, right? Because remember, before the extension, this used to be external. And we convert that into internal. So we're only adding 1, but no minus. All right. Number of internal nodes plus 1. And then this part here, the +1 is also corresponding to n. And if you look at it, it makes complete sense. For the same node, n here cannot be external, internal at the same time. That's why -1 and +1. So they will balance out. Right? And also the 2 additional nodes, exactly the size is incremented by 2. Right? Good, we're almost there. Let's now try to see if this equation will hold. So far we got number, you can think about 1, 2, 3, and then this will be step number 4. Final step. We want to show this one here. Okay? So what I will do is, let me start with number of external nodes after extension, okay, by equation 1. It will be this, number of external nodes plus 1. And then by the inductive hypothesis over here, this is going to be equal to, by inductive hypothesis, ni plus 1, and then don't forget a +1, right? All right, and then, not done yet. You can see this part over here, ni plus 1 is ni prime. All right? I'm just trying to go over with your math, but of course, you really got to see if you can redo it yourself and or make sure it completely makes sense. And this one here by equation 2. ni prime plus 1. So what we have is ne prime x exactly equal to ni prime plus 1. All right, done. There might be like a different ways for you to really argue about the numbers, but I'm presenting to you what I think will be the clearest way, because you're very clear about how many nodes I have for internal, external, before and after extension, right? Questions about this one here? So now, so far we have seen 3 mathematical inductions, right? So I think you can see they really follow the same pattern. What's going to be the most creative part, which will be tricky, is starting from number 3. Once you got inductive hypothesis, you want to imagine what a cloud or the tree is, and then think about extension. It's always the case, right? Of course, that'll be the trickiest part to get right, depending on the problem itself. Okay. Okay. We got about 20 minutes. I would suggest, I definitely want to give you a little bit, like a walkthrough. Not really exactly walkthrough. I want to talk about how you can create like a binary tree, which you will see a lot in the assignment number 1. Let me talk about it. That one might take about, hopefully, only 10 minutes. After that, I can briefly talk about how you can do rotation for deletion, which might give you a little bit more inspiration for assignment 1. Okay, you can think about that some extension you can do for assignment 1 later. Okay? But if I cannot, again, I got video. I can definitely post it. You can also go over. Right? But at least I can talk about assignment 1. Okay? Okay, so let's now talk a little bit about assignment number 1. So I'm not really importing the Java project into Eclipse. That's something I know you guys know how to do. We kind of walk over the steps in the previous tutorial. I want to talk about the BST node class and also one code fragment you will see a lot in the starter test. Okay, so let's look at it here. Okay, BST node. Okay. Like what we said earlier in the lecture, we got key and we got value, and we assume that key is always an integer, right? For searching purpose. Of course, for your own application, you can also make the key maybe another generic parameter, but you gotta say it's comparable, but it's outside the scope for this course. But if you want to do a little bit more Java exploration, you can do it. Okay. So every node has a parent, has a left, and also has a right. Okay. So there is one reflection question I put on one of the JUnit test cases. You want to think to yourself, whenever you are inserting or building the construction for the tree, how are we setting especially the left and right and also parent reference properly? You want to think about that. Maybe something already done for you in the BST node, or maybe it's something you have to do by yourself, right? Just think about that question, right? Important, okay? And we got two constructor, right? Either you can use this one here or use this one here. That's also something we said earlier, but let's just do a quick review. So you can think about right here, this one here is for creating an external nodes, which means we don't pass any key or value, key or data. So this will be for external nodes. Okay. On the other hand, what you will see a lot will be the constructor for creating internal nodes. Okay, let me just do a little bit better. It will be all the way to here. All right, this one here. So that one is for creating internal nodes. And what should we pass? Remember this sequence here, because we're going to need that. Key, followed by data value, followed by the left, and followed by the right. Notice that we didn't pass any parents reference over here. Notice that, all right? That's related to the reflection question you want to think about. Right? I'll leave that open for now, right? Think about it, okay? And then you can see that over here, we're trying to set the key value, and also the parent will just be null for now, and then left, right. And also bidirectional. This part here is also very important, okay? This part over here is saying the following. Let's say the current node is right here. And then we are saying that its left is, okay, this will be the left reference is setting to the left parameter, right? You can think about this another left reference over here, right? You're saying this, the left, is pointing to the same as the left parameter. In addition, we got to make sure bidirectional, left, the parent is also set to be this. All right, that's important, bidirectional. If you didn't have that, it wouldn't work. But luckily, I gave you that already, right? I don't want you to struggle too much about this kind of subtle details. So that means this part over here will also to be the parents. All right, that's something you really have to pay attention, okay? All right, you do the same thing for the right. Let's now look at this part over here. Somehow I decided that I want to be nicer to you guys. I actually put some indentation, new line. This could have been a one-line expression. Could have been. Agree? So maybe in the test I should do that. I'll give you one long line and then draw the tree accordingly. Okay, I could, right? But for now, let's be nice, just to see. Okay. This way of creating like a recursive object is very common. Right? I want to show you maybe something you haven't seen before. If you haven't, now it will be the time. Okay, it's not bad. Okay. First of all, we are saying that we are having some expected BST node, which will be the root of some binary tree. And then starting from here, whole thing single semicolon. So that's why I said it could have been a single line. All right. Let's now see how we can decipher this. It's not bad. Okay. First of all, you can see that we do have some external nodes. This one here. This one here. Also this one here. This one here. Also this one here. This one here. Also this one here. And also this one here. All right, so these are the external nodes. And we also have internal nodes. The top level, this will be internal. This will be internal. Oh, actually, I left one. This will be external. Right? And this will be internal over here. Internal. Internal. And also internal. Also internal. And internal. So you can see we're calling either the constructor for internal node, we're calling the constructor for external nodes. But now the question is, how do we visualize it? This is how I would do it. Okay? This will be the root. Okay, let's do it right away. 44. Right, so I also make the data value like a string, just the same as the key value for simplicity, right? So 44. And think about indentation here really helps. This part here is the left subtree. And this part here is the right subtree. All right. Left subtree, somehow quite easy, right? The left subtree has the root, 17. And then it has further left subtree, which is external. And also right subtree, which itself has further root, 32. And then further left and right. Follow? Okay. Why don't you guys take 1 minute? How should the right subtree for the whole thing look like? Give it a try. I think this might be the single most important thing to get right. If you don't even understand how to read this tree, there's no way you can complete the assignment, right? While you're trying, we should really think about what if we didn't have such a mechanism to write one single line of the tree construction. Think about what you got to do. Let's say there are 50 nodes in the tree I want to have. I got to create all the 50 nodes in isolation, and I got to set the left and right accordingly, separately, something like that. Not so pleasant. Also not as easy to really keep track. So I think this single line here with a new line and also indentation is a very nice way to show as part of the test case, what we're expecting. Okay. But indentation here is not exactly perfect. I should really fix that. I just noticed. Well, but you can see the point. Okay. All right, let's now do it together. Okay. Right here. Let's try. So here, the root, 78. And then left subtree, over here, and also right subtree. The right subtree will be just 88 with two external nodes. And what about left subtree? Over there, the root will be 50. And then 50 here. And left subtree, the root 48, two external nodes. And then right subtree, 62. And then we have two external nodes. And don't be too surprised, this tree is one of the examples we use in the lecture. I encoded that explicitly. All right. Any questions about reading trees like this. We okay? Right, I think you'll get used to it. And then I think, I really think this will be the way to go if you want to scale up, the assignment project, right? You really want to have a good way to really specify the tree structure in a single expression. Of course, you got to use new lines, indentation for human to read, right? All right. I think we got about 10 minutes. I think I cannot really do the whole deletion example, but at least we can do some. How about this? It's really your time. I don't want to waste it. How about 10 minutes, okay? The deletion example there, okay? So that'll be the steps that we went over last time, and then we spoke about they might be up to, log n rotations that we have to do for deletion. And we got two cases, right? I will just show you enough so you can see how the two cases can be judged. I think that'll be enough for today. Can we just have you do the following, okay? How about we start step by step? Let's now first create. You can do along the way. Let's not waste time, okay? Let's create a BST by inserting. And the way we insert is just like insert for BST method in your assignment number 1. That's one tip. So when you're trying to do insertion over here, we're not really talking about balance just yet, not yet. When we say insert for balance BST, another method, you have to worry about rotation to restore the balance, right? There are two separate methods, okay? Okay, let's do it right here. So we start with part A. So we got 50, and then 25, and then 10, and then 30, and then 5, and then 15, and then 27, and then 1, 75, 60, 80, and then 55. If I make mistake, please do let me know. All right, that's after all the insertions. Good. Is it balanced? Check balance, okay? Let me do the balance as we did earlier, just to brush up, and then I'll give you a little bit tip for assignment 1, which somehow written in the test cases, but I'll also mention that, okay? So 0, 0, 1, 0, 1, 2, 0, 0, 1, 2, 1, 3, 0, 0, 1, 0, 1, 2, 3, 2, 4. 0, 0, 1, 0, 1, 2, 0, 0, 1, 2, 1, 3, 5. You need to be faster than me in the test because there will be other questions you have to worry about, right? But you got to practice, okay? All right, so that one's balanced, right? You can double check, right? So now, in the assignment 1, especially for insert for balance BST method, right? Let's say after inserting all these, right? If you really want to check, let's say if the tree is actually balanced, right? So there are two ways to do it. The way we are doing is really for bottom up. We're trying to annotate each node with the heights. If you want to follow this approach, which is totally intuitive, which I will recommend, maybe beyond the scope for this assignment. In that way, you have to extend the BST node class with one more attribute called heights. However, I wouldn't recommend this approach for assignment because in the programming test, you will not be allowed to touch the BST node class. The compromise I would suggest would be for assignment, you can easily just define a helper method to say, given a particular node, what's the heights? Okay, that would be simpler as well for your logic, right? Of course, this second approach here is not as efficient because you will see exactly, right? You can think about why it's not as efficient because every time you want to calculate the node height, you're not really accumulating bottom up. You're just calculating from scratch. Not as efficient, but that's okay. We can deal with it, okay? All right, quick thing for you to do before I show you the answer. Delete 80. Well, this one is obvious, actually. Well, Of course, you can, this particular example here, the deletion is actually the simple case because AD here is really the internal node with both children being external. It's actually case number 2, right, for the deletion. But there is possible maybe the actual, another question, there might be case 3 or even case 4, right? You want to be sure you can do it, right? That's the example we cover elsewhere, all right? So what we do is we're going to delete. Delete 80. And what I will do is I will try to copy this tree. Okay, that's pretty good. Okay, and then, so this would be 2. Okay, that'll be fine. So if I want to delete 80, all I do is I simply, there's something I want to say, okay, quickly. I'll make a note for you. So if you want to delete 80, that would be case number 2, right? You can refer to it, right? The slides, case number 2. And let's simply now delete the node, right? And that one there is going to be put into external. Right, let's update the heights. 0, and then 2, 0, 3, and then actually, you can see that this is 0, maximum between 2 and 0 is 2, plus 1 will be 3, right? However, is the tree unbalanced or stay balanced? Diego, unbalanced? Tell me the lowest node that's unbalanced. 75, exactly, because we got 2 and 0, right? All right. So now here comes the important point. I want to make sure I do it together with you, okay? So here we have A. Lowest node, lowest unbalanced node. All right, so in this case, you can see between 2 and 0, the difference is larger than 1, okay? It's unbalanced. And according to the cases over here, you have to find the taller child for B. And then between H1 and H2 for C, we want to see whether or not these two are the same heights, or simply choose a taller one, right? These are the A, B, and C. Okay. So you can see A is here, and then for what should we choose as B? Taller one, right? So choose the 60 over here, right? This is the taller child. And then for C here, we got to be careful. You want to look at the heights for these two nodes. This node here and this node here. So which case are we dealing with? 1 and 0, different. So choose the taller child. So we're going to choose 55. Right here. All right. So this will be B, and this will be C. And we got to do a rotation. Right? You can see the slant the same way. So we're going to do A. So you can think about this slant this way, to the left. So we want to promote the middle node B up. So it's going to be a right rotation, right? That's something you will have to do for like after insertion for assignment 1. It would be similar, okay? So let me write it down, and then I think that's good, okay? So here you want to think about you're basically doing a right rotation on B. So after this rotation here, you will see a new tree. So what's going to happen is this middle node, this middle node, yeah, give me 1 minute, I'm done. Okay, 1 minute, will become the root. And from there, search up to find another unbalanced node. If you can find any unbalanced node, the lowest one, do another rotation by following the same step. If you cannot find any more unbalanced node, you're basically done. But in the case of deletion, you have to do these repetitive steps. Right? Right, I'll post the video as well, so you can feel free to follow through to see how the tree should look like after the 2 rotations. All right, thank you so much. I'll see you guys next Monday.